Good morning. This is Dr. Doobie again. I'd like to talk to you for a minute about Excel. We use it a lot in this course. Is this course about Excel? And how would we be tested on this in a classroom exam? Let's talk about that. This is a course on separation processes, like distillation. We might have a stage that we feed to, and it will have a vapor leaving that stage and a liquid leaving that stage. Each stage is described by two mole balances and two equilibrium relationships. That is, if we have two components we're separating. Each stage, by the way, has its own temperature. Now, more often than not, we combine those into multiple stages. So we'll have a stage above and a stage below. Each one of these has a vapor leaving it and a liquid leaving it. And there might be many of these. Each one is described by its own equations, generally two mole balances and two equilibrium relationships. And you know that as we pile up more and more stages, we have more and more equations. Not only that, but these equations here depend on these equations. These equations depend on these equations. And so very soon we have a lot of equations. These equations are generally algebraic, we're not really dealing with differential equations, for instance. They're coupled because one set of equations depends on the other. They're nonlinear Why is that? Well, these equilibrium relationships oftentimes are not linear. For instance, if the K value is determined with Antoine's equation, that's an exponential equation. If it's determined with a polynomial equation, that is a power equation. And so they're nonlinear. And they are multiple. So there's many equations that have to be solved simultaneously. So we have multiple algebraic coupled nonlinear equations. We can't solve those by hand. We have to have some kind of tool to solve those. So what kind of tools do we have available? Well, we could solve things by hand. Back in the day, I still used a slide rule. Don't recommend that. The trouble is, if you look at the time to solve a problem versus the number of stages, you might be able to solve a problem, a single stage problem, in a reasonable amount of time. You know, maybe a single stage can be solved in a couple hours by trial and error or some more efficient method. But that time just goes up and up and up exponentially as you have the number of stages increase. You don't want that. Well, you could write some kind of computer program using a computer language like Fortran, C++, Python. I'm not even sure what Python is, but it's a programming language a lot of people are using these days. And if you're expert at these programming languages, that's one possibility, to write some routine that will solve these kind of coupled programs. But really, in engineering, most programs don't even teach computer programming anymore. We have some programs like MATLAB, CAD, MATLAB. So these would work. These can be used to solve engineering problems. And if you happen to be good at these and are comfortable with these, why not? And I certainly do not think that you need to use Excel. I happen to like Excel better. But if you like these better, by all means, solve these problems with those kind of tools. But I happen to use Excel a lot. And I have these set up under the Excel page for all the problems in the book. And so they're already built, they're already solved, and you can use those as templates for other problems. So for instance, this is a two-stage distillation column that I built for the ethanol water tutorial. So you look under the tutorial tab, you'll see the ethanol water example there. And I show how to use polynomial functions for equilibrium, the T, X, Y equations. And actually there I split the bubble point and dew point curves into portions because one polynomial does not fit them very well. They have to be split to get a really good fit. Anyway, I explained how to use this, but the point is you could solve any problem, two-stage problem, that requires a polynomial function for equilibrium by just simply substituting in the constants for that system. And you don't have to go to the trouble of building a whole new spreadsheet to solve that problem. And you can do that for ideal solutions that have Antoine's equation, just replace the Antoine's constants. Not only that, it's pretty easy to build graphical representations of solutions in Excel. In fact, this solution here to that two-stage problem shows the leaving streams, which are in equilibrium, so they're on the equilibrium line, and the passing stream between these stages. And here is the composition of the stream leaving the top stage, and here's the composition of the stream leaving the bottom stage, so that you can see the stair step forming. But the neat thing is, the way this is set up, it calls these values from the spreadsheet solution. And so if I change the reflux ratio or any other factor in the problem, the solution, graphical solution, changes automatically. And that's a really cool thing because you can play with the problem statement, make changes to it, and see graphically what the happens to the solution. So that leaves us with the question, how would you be examined if you can't use Excel actually in a classroom exam? Well, there are two general ways to examine you on these problems. One is to set up the equations exactly as you would do in a problem to get it ready for Excel. Now, in my exams, I take students through all the steps, and so first I'll ask them to draw a PFD, and it's surprising sometimes that people have trouble going from a problem statement, like a story problem, right, to a picture of the process. So that's a very important step. Then perform a degree of freedom analysis. So you recognize what are the knowns and unknowns in a problem and what equations do we have to find their values. And then finally, C, write the equations down. Now, here we would just write them as you might put them in Excel. So for a total material balance, for instance, you might write that the feed plus the vapor coming in from the stage below, say VI plus 1, plus the liquid coming from the stage above, I minus 1. This is equal to the vapor leaving that stage plus the liquid leaving that stage, and on and on. You also would write down the equilibrium relationships. So Y is equal to Kx, where K is, the Antoine's equation, A minus B over T plus C, and then all over the total pressure. Something like that. And you'd write down all the equations that would need to be written to solve the problem. The other type of problem, so right up here too, interpret the graphs, interpret the results. Sorry about that. Okay, so in this case, you might be given the results from a particular process. This is that two-stage ethanol water distillation column. And maybe I would show the PFD for this process and ask you to identify which of these are the what is the vapor composition leaving the top stage? What is the liquid composition leaving that top stage, etc.? Where did you find that on the graph? What is the composition of the passing streams between stages, and where did you find that on the graph? Also, I might give the TXY diagram and ask you to identify the temperature of both stages. So the intermediate step between writing the equations and interpreting the results is that Excel solution, but it's really not practical most of the time to put that on the exam. So you just have to learn how to do that in the example problems and in the practice problems. So I hope that tells you a little bit about my philosophy about what Excel is. It's just a tool that you use to solve these problems.